Up to this point, we have been talking about series in which the terms are all positive terms, and in order to converge, we know that those terms need to approach zero. We're now going to talk about series in which the terms alternate in sign, positive, negative, such as this. So that can be of one of two forms. They can start off negative, positive, or start off positive, negative. And so our series are of these two forms. You'll notice that we use -1 to an exponent to change the terms between positive and negative. So these are called alternating series. Now remember that we've talked about the harmonic series in the past, with terms that look like this. And remember that even though the terms of the series approach zero, we've shown that this series diverges. If we look at the sum of n terms, we can see that the sums in our table continue to grow larger and larger without bound. And so we say, because the sequence of partial sums diverges, that our infinite series diverges. You look at it graphically, you can see that the sums continue to grow larger and larger as k gets larger and larger. So the harmonic series, we know, diverges. But what I want to look at now is the alternating harmonic series. And my terms here would be 1 minus a half plus a third minus a quarter plus a fifth, etc. And we want to look at whether this converges or diverges. And if I again look at my sequence of partial sums, the first two terms add to a half, the first three terms add to 8.3 repeating, etc. And if I continue to scroll down, it looks as though the sequence is narrowing in on some number. In other words, it looks like this sequence is converging. Let's look at it graphically. As n, or I'm using k in my formula, is getting larger, my y value is my sum. My sum is narrowing in on something 0.6, something between 0.6 and 0.7. It seems like it's narrowing in on something. It seems like it's converging. So it seems as though the alternating harmonic series is converging, even though the harmonic series diverged. And in fact, the alternating harmonic series does converge, which raises the question, how are we going to know whether an alternating series converges or not based on the tests we have? And so we have a new test for alternating series called the alternating series test, which says that if you're given an alternating series of either of the two forms we talked about, if you can show that the terms are decreasing, that's the positive part of the term is decreasing, after some point, so eventually, so you get to a certain point, and then from that point on all the terms are decreasing, and if you can show that the limit of the kth term is zero, you can show these two things, then you will know that the alternating series converges. So let's use the alternating series test to show that the alternating harmonic series converges, as we think it does, having looked at it numerically and graphically. So the first thing we need to do, first condition, is to show that the terms are decreasing. So we need to show, number one, that the k plus first term will be less than the kth term. Well, the kth term is just this positive part, not the negative part, that's the alternating part. So 1 over k, is that going to be bigger than 1 over k plus 1? Well, as k gets bigger, the denominator here is going to be larger, which means the value of the left side will be smaller. So that, in fact, is true. We can see that. Second of all, I've got to test the limit as k goes to infinity of a sub k, which is 1 over k. And as k goes to infinity, that's going to go to 0. So both parts of the alternating series test are met, and so we know that our original series converges. Let's write this up. In our given alternating series, okay, so we need to acknowledge that it's an alternating series. 1 over k plus 1 is less than 1 over k for all k. greater than or equal to 1, that is. And that's what we need because it's what our index is. And the limit of that is 0. Therefore, by the alternating series test, our series, which is the alternating harmonic series, it's an important series, therefore it converges. Here's another example. If k starts with 2, my denominator would be 2 minus root 2, which would be a positive number, and my sign on that term would start off being positive. My next term would then be negative, positive, so I do have an alternating series. So the first thing I need to do is check that my terms here are decreasing. I think I can see though that if k increases, this will become bigger than this, and so my denominator is going to continue to get larger, and so my terms should decrease. But if you're ever uncertain or not completely convinced by that argument, you may need to look at some other things. So what I'm going to do is I'm just going to consider this as a function and look at its derivative. And if I can see that the derivative is always negative, then I will know that the terms of the series are decreasing. So the derivative of this, if I use the quotient rule, is the bottom function times the derivative of the top minus the top times the derivative of the bottom. Now if k is greater than or equal to 2, as it is here, I can see that the denominator of the derivative is always positive. And if k is more than 2, that's going to mean this is positive and this is negative. So the value of the derivative is going to be negative everywhere. So since I know for k greater than or equal to 2, therefore I know that my terms are decreasing. Okay, so I've met condition number 1 of the alternating series test. The second thing is I need to do the limit as k goes to infinity. I have infinity minus infinity on the bottom, so I'm going to need to do some manipulation to determine what's going on. That's an indeterminate form, we know. If I factor out root k, that's going to be root k minus 1. And this is positive infinity, and this would be positive infinity, and 1 over infinity would be 0. So I know that the limit of my terms goes to 0. And so it looks like we have shown the two conditions needed to show that this alternating series converges. So let's write it up. In the given alternating series, I have shown that the terms are decreasing, so I can say that nicely like this. And the limit therefore, by the alternating series test, my given series converges. The next thing we want to look at is how to approximate the sum of an alternating series. So what I'm going to do is go back to the alternating harmonic series, which I was showing numerically and graphically on the calculator earlier. And I've got a table here showing the value of the kth term of the series, as well as the sum of k terms. So, for example, the sum of the first 2 terms is 0.5, the sum of the first 3 terms is 0.83 repeating, etc., etc., etc. And I'm also going to show this sum visually. So I'm starting off at 0. My sum is 0 to start with, and after the first term I can see that my sum is 1. Right there, the sum of the first term is 1. So what I've done here is I've added on term 1. If I then add on term 2 from that point, which is a negative value, so I have to go back 0.5 of a unit, I land at S2. I'm then going to add on term 3, which is a sub 3, and that's going to land me at S3. So I've added on a sub 3. The sum of 3 terms, add on a sub 4. and that's going to land me at S4, so A sub 4. Here's an animation of what I'm trying to show from the Wolfram demonstration site. So hopefully what you can see is that our approximation for the sum of the series is narrowing in on a smaller and smaller interval as the number of terms that's added on increases. And we can see that our actual sum is going to end up being between two consecutive sum approximations. So our sum is somewhere in here. And because what we add to go from Sn to Sn plus 1 is A sub n plus 1, whether we're adding or subtracting it depending on which term we're at, we can see from this that in either case, the difference between our estimate Sn and our actual sum is going to be less than the next term that we don't count in our estimate. In other words, the error between our approximation Sn and the real value of S is going to be less than the first term that we don't count in our estimate. And this is called the error bound for alternating series. Just to apply that directly to my example above, if I was going to estimate the sum of my harmonic series using 5 terms, I can see that S5 from my table above is this value, 0.783 repeating. How accurate is this estimate? We can use our error bound to find out. So we can't find the actual sum S, but we know that S5 is this value, and we know that this error will be smaller than the 6th term of the series. And the 6th term of the series, looking back on our table, is 0.16 repeating. Remember, we're taking just the positive part of that, also because we have the absolute value signs here. And so our error is this much, which means that the actual sum add 0.783 repeating to both sides means that our actual sum is between 0.62 and 0.95. So based on using 5 terms, the sum of 5 terms, we know that the actual sum is somewhere between those two values, which is still fairly large. So then you might say, well, what if I wanted an estimate for my sum S that was accurate to 2 decimal places? Alright, so in this case we're saying that our error to 2 decimal places means that with rounding our error can be at most this. So our actual sum minus our approximation we want to have be less than this value. And since our error bound formula, our error is less than the first missed term, we basically want to find n so that this is as close to 0.005 without going over as we can get it. In other words, we need to solve an inequality. So the n plus first term of our series 1 over k would be 1 over n plus 1. I can write my decimal as a fraction, 5 over 1,000, which is 1 over 200. And we have positive values on both sides. We can use a property of inequalities to reciprocal both sides and flip the sign. And so n is greater than or equal to 199. So if we use 199 terms, if we add up the first 199 terms of our series, we will get an approximation for the alternating harmonic series accurate to at least 2 decimal places.